Hello everyone. In the previous video we learned about regression using the linear method, lasso, ridge, elastic net, and the goal of the regression was really to estimate the output value of an underlying function that we try to model for a given test value, right? So it is really a supervised learning method. Here today we're gonna talk about another category of regression, which is not really a linear regression. It's called the logistic regression, which is using a sigmoid function. And you cannot, as I said, categorize it as linear. You'll see it is going to be a nonlinear regression. And although the goal here is again to predict the output for a given test input, right, and to estimate the underlying sigmoid function, we really use this regression for classification purposes. Why? Because the output of this function, if you look here on the right hand side, the output of this function for most of the range of the independent variable, right? So here, if you have, let's say, your x and the y-axis, correct? And the origin is here. So let me use an arrow. Didn't go too well. So here, right? This is one axis and this is another one. So if this is x and this is y, then for most range of x, you see that the output y is either 0 or 1. Okay, therefore, you can, if you have any specific x value you want to test the output for, let's say here at this green point, for example, if you project it onto this function, you see the output is going to be quite close to either 1, or let's say if it's here, for example, if you project that, again, you see it's actually quite close to 0. So except for some small range here in the middle, most of the outputs are either 0 or 1, and that's why you can use binary 0 or 1 classification. So, and the way you can do the classification is to compare the output at the test input against half, which is exactly halfway between 0 and 1, right? So say if this output is bigger than half, you can call it 1, and if this output is less than half, you can call it what? You can call it a 0. Okay, so you can also basically classify a given test input as belonging to class 0 or class 1. Here you see class 1 are shown with the red dots and class 0 shown with the blue dots. Now the important thing is this: if I give you a bunch of numbers x and the output y for them, can you estimate this logistic function, the sigmoid function for me? First of all, you might say, well, what kind of function is that? Well, this is the type of the function. 1 over 1 plus e to the negative a times x minus b. If you see here clearly, when x goes to positive infinity, so the numbers are getting bigger, this is going to be e to the negative infinity, which is 0, so you're going to get 1 over 1, so you get 1. On the other hand, when x goes to negative infinity, now in the denominator you have e to the positive infinity, which is infinite, and 1 over infinite is going to go to 0, as you can see on this side. Right, so this is x going to negative infinity, here x going to what? Positive infinity. In the middle, it changes between 0 and 1, and exactly in the middle, if you want, right, at x equals 0, the value of the function is 1/2. as e to the 0 is 1. So it's going to be 1 over 1 plus 1. So here, right in the middle, it is 1/2. That's why we said we compare against 1/2. Bigger than 1/2, you say it's 1. Less than 1/2, you say it's 0. Okay, so this is the function. Now, can I, with my training data in blue and red, can I estimate the two unknown parameters, a and b, right? These are the two parameters, the unknown parameters of this function. If I find a and b, then I found my function. Can I find a and b through simple linear regression? The answer is no. Because if you call this equal to y, there is no way that you can rearrange the relation between y, x, and a and b as a linear relation in terms of a and b, right? You might say, well, what I can do is first I invert both sides, so it's going to be 1 over y is 1 plus e to the negative a times x minus b. Then I take 1 to the other side, so now it becomes something like this. Then I take natural log of both sides, so it will be natural log of 1 over y minus 1 is negative a times x, and then plus ab, correct? If you multiply that negative a by the whole parentheses. So now, even if you call this a new data like z, which is a function of y, now z is given, x is given, right? Can I here say the relation is linear? No. Why not? Because, as you can see here, I have the product of the two parameters. I have the product of the two parameters, and for that reason, I cannot write the relation between z, x, a, and b as I told you, some a of x times the function, the unknown vector a and b, to be some other function of y, or in this case z. I cannot do that, so I have to do a nonlinear regression. And I know some of you might say, well, consider this ab to be a parameter like c. So now the relation is linear, negative ax plus c. That's true, but c, remember, c is not independent from a. You can do the linear regression when you can independently change a and c. But c is clearly a function of a, right? If I bump up a, c goes up automatically. There is correlation between a and c, perfect correlation. So that does not allow me to perform my linear regression. So how do I do it? Well, the cost function here that you use to minimize is the cross-entropy. If you go back to one of my first videos on machine learning, right, when I talked about the prereqs, one of the topics that I talked about was cross-entropy here. And so please refer to that video. And the use of cross-entropy was to measure how far two discrete distributions are away from each other, how far away they are, okay, the distance between two distributions. And it was negative of summation of p times natural log of q, where p and q coming from two discrete distributions, p and q, okay, pk and qk. So now, can I apply the same notion here? Yes. So here you have on one side data y, the other side you have p. Y's are your actual data points and p's are the estimated data points, right? These p's are like y hats. So you want to know the distribution of the data y's and the distribution of these y hats, how close they are to each other or how far away. You want to measure a distance. So that's why you use the cross-entropy formula. And here we want this distance to be minimized, not maximized. That's why that negative sign that we had, we neglected it. Or we kind of absorbed it into the function by, instead of maximizing that, we're trying to minimize this with positive sign. And you might say, well, where is the second term coming in? It's because you have two classes of data. You have one class for which yi is 1, and you have another distribution for which yi becomes 0. So the first term that you see here, this guy, is to measure the closeness of distribution of these yi's for which y is 1 to their estimate data, the y hats. And the next one here is for this category for which y is 0. And since you cannot just multiply the zeros by the natural log of the p's for these points, because then all of this term is going to be 0 and does not contribute anything to your cost function, that's why you are doing what? You're subtracting 1 minus y. The same thing, subtracting 1 minus the estimated y hats for them, natural log of that, and you add it to the original terms. Okay, so again, if I had to use the p and the y for the class for which the data is about 0, the output, actual output or the estimated output, then this whole term will go to 0. And so the error in this left side, in this class of 0, will not contribute anything to my cost function. So I had to do 1 minus y, so this term is non-zero. Okay? So these are the errors in either classes. You add them together, or not error, really, the entropy between estimated data and actual data, and now you add them together. Clearly, this guy is a function of what? Function of your parameters a and b. And you might say, where is a, where is b in this formula? Well, a and b are hidden in this p. Right? The p's that you calculate, remember, p is a function of a and b. So when you calculate p for any data point you estimated, you definitely have what? A and b in it. And you want to choose the a and b such that this function is minimal. How would you do it? Well, you take derivative of j with respect to a and b. Now, the y and 1 minus y are just constant numbers, so you treat them as constant. So now what is this? You're going to take derivative of this guy with respect to a, let's say. Well, you have to use the chain rule, right? Because you are doing partial of natural log of p with respect to a. So you do it as partial of natural log of p with respect to p first, and then partial of p with respect to a. Actually, this is like d, not partial, but this one is going to be 1 over p, and this one you have to calculate. So the 1 over p term that you see here is because of the natural log derivative. Similarly, on the right-hand side of the j, 1 minus y is treated as constant. Then you have partial of this natural log of 1 minus p with respect to p, which is u prime over u. In this case, the derivative of 1 minus p is -1, and divided by the whole thing, which is 1 minus p. So this term that you see is, again, this guy here, right? And now, where is the rest of it come from? This one and this one. Those are the partials of p with respect to a and b. In the top equation, they are both partials of p with respect to a. How do I get it? Well, I use my basic calculus knowledge. If this is p as a function of a, what is partial of p with respect to a? It's a ratio. So here I did some math manipulation, and you can show that the partial of p with respect to a for the sigmoid function is p times 1 minus p times x minus b. Similarly, partial of p with respect to b is going to be negative a times p times 1 minus b. So you use those guys. You see this one here. Look at that. You can see it here. And then this one, you can see it here. So if you do that, what would you get as the result? The results are going to be these two equations. This is one after you do a lot of simplifications. This is one. This is the other. These equations 1 and 2, if you can solve them, they should give you A and B. You have two unknowns and two equations. But these equations 1 and 2, although they look dangerously simple, they are not that simple. They are clearly nonlinear equations. Why? Where is A, where is B again? You might say, where is A, where is B? Well, they are hidden in this P, right? This parameter P that you see in both equation 1 and 2, this guy, here and here, those have A and B in them. So here at the bottom, I expanded equations 1 and 2. First equation 2 here, then equation 1, I expanded them in terms of what? A and B, and if you look at them, clearly they are both nonlinear equations, right? Look at that. One equation is like this. Clearly the equation is a function of your xi, the data point, yi, the desired output, A and B, and equation 2, which is this one, again, similar thing. So now, to solve both coupled nonlinear algebraic equations at the same time, and here I use the Newton-Raphson method, and for Newton-Raphson we use the update equations. Here I have expanded these update equations for you if you want to implement it yourself, but I also have a code that goes with this lecture, and in this code I have provided some 15 data points, 7 of them belonging to the class 0 and 8 of them for the class 1. And this is my function, and here I use Newton-Raphson. I estimate both A and B, and I plot the functions for you with the final values of A and B that I found. And then we can test for a test point, like for example 3.2. Feel free to change this number to anything you want. Then if this number is bigger than 0.5, I say the class is 1. If this output is less than 0.5, I say the output is what? 0. Now the output is not really 1 or 0. I have to say the output class of this data is a 1 or 0, because the output is going to be somewhere between 0 and 1. So let's go ahead and run that. Here we go. You see it actually converges quite fast. And for this set of data that I have, as I said, 7 red, 8 in blue, A is 15.48, B is 0.71. And if you go back to MATLAB, you see that it says class 3. The class for the data at 3.2 is 1. And you can see why, because if you look at 3.2, right, it's somewhere here, and if you project it, the output is almost what? Almost 1, almost perfectly 1. I mean, like if I go ahead here and use my data cursor, I don't have really anything at 3.2, but you see at 2 it's almost 1, and at 4 it's almost 1. So at 3.2, if I want to really know what's the value of my function, I can pass it to this P and say, what is P for the given A, B, and the X, right? So let me just do that for you. So the final A, I call it AA, BB, and XX. So if I want to know the exact value of it is, you see the answer is what? 1. And it could have been obvious because this is quite a bit here to the right side of the middle point, right? But if I go with a data that is kind of in the mid-range, right? So somewhere between, let's say, 0 to 2 or 0 to 1 point something, right? For which the output is not perfectly 1. So let's say I decide to go with 0.8 instead of 3.2. Then you see the output is 0.805, and since this is bigger than what? Bigger than 0.5, then I should declare that point a 1. Say at x of 0.8, the class output is 1, okay? And here you go, you see? So this is how you can now classify any point as either class 0 or class 1. That's why we call it binary classification. And this is how we perform this nonlinear what? Regression for this sigmoid function. So hopefully this video was useful to you, and you can download this demo MATLAB file. Feel free to change your data points and use the Newton-Raphson solver to give you the underlying sigmoid function. Thank you so much for your attention. I will see you in my next video.